Hello everyone, today I would like to talk about some computational designs of materials, machine learning with human learning. I believe many of you have heard Materials Genome Initiative. Its purpose is to combine computational, experimental, and data science tools together to speed up materials innovations. This topic is so popular right now. In 2018, there's one whole volume of MRS bulletin was dedicated to this data-centric science for material innovations. But here, I would like to share some of my understanding and recent research examples from my groups. The first question I want to ask myself is, what are the special features of data-centric science in MSc? Compared with many other data-centric science in machine learning applications, I think there are two special features. First, the data sets are very small. This is essentially because of the high cost to get data for MSc, no matter from materials synthesis and materials characterizations, and also computer simulations. Fortunately, there are already some available high-quality database, like the Materials Project based on quantum mechanics calculation, ASM Alloy database based on thermodynamics and phase diagrams, and Sign Glass database for the oxide glass properties. Another feature of data-centric science in MSc is that we have to include in the physical mechanism into our models. So in my understanding, we can think this problem in this way. For all systems we study in nature, we can divide them into three levels. On the lowest level is individual atoms and molecules. The number of particles in this system are small, so the degree of complexity is relatively small. We have a lot of understanding on their physical mechanisms. The application of data-centric science tools is not so urgent. On the other hand, on the other extreme, like a biologic system, the degree of complexity is very high. So we heavily depend on data-centric science tools. However, because we have less understanding of physical mechanisms, this tool are maybe not very reliable. The materials is a perfect example in the middle. On one hand, we know many things about their physical mechanisms. On the other hand, it is still too complex to derive analytic models. So we hope the data-centric science tools combined with the physical mechanism can speed up our understanding and prediction for new materials. So today, I would like to give two examples in this corresponding to these two features. The first example is predicting densities and the elastic property of glass by machine learning, which more focused on how to generate and use the data. And second example is the correlation between electronic structure and solute defect interactions in metals, which is more related to how to use physical mechanism in our learning process. So first, I would like some of the funding agencies from Continental Tech Gift and also from University of Michigan Staff Funding and the NSF Career Project, and also thank all my group members and collaborators, especially Dr. Yongjae Hu, who is the first author of the two papers mentioned above. So for the first problem, we want to design the advanced silica-based glass to achieve some special functional structural application purpose. So this silica-based glass can be used as a structural fiberglass as a critical component in composite materials. If we can achieve high elastic modulus and a low density for those glass, we can generate composite materials with a better strength and a light weight. That is not an easy task because there are large design space of composition. There can be more than 10 types of oxide including in this glass design. More importantly, we know glass are amorphous materials. The densities and the elastic modulus may be complex function of many features beyond the chemical composition. So fortunately, we can apply computer simulation like MD molecular dynamics simulation based on reliable interatomic potentials. In those MD simulations, we initially put different type of atom together. Then we increase temperature to melt this system, like how we make a real material glass in the real world. Then we crunch it down step by step until we get some stable glass structure at room temperature. Then we apply different kind of mechanical deformation, which can generate correspondingly different kind of elastic modulus, like bulk modulus, shear modulus, and Young's modulus. We know for the isotropic materials, for the three modulus, only two of them are independent. If we know any two of them, we can obtain the third one automatically. So the case is that if we only want to study glass composition, like 10 or 100 different kinds of glass, we can directly apply those MD simulation to calculate the density and the modulus for this different glass one by one. But the problem is that those simulations still take a lot of time and resource. So it is impossible to apply such MD simulation to fully explore the totally new composition space, because the computation cost is still too high. So our target is to build up a machine learning model to predict the density and the elastic modulus for multi-component silica-based glass systems. Like other machine learning model, this can be achieved by three parts. First, we need to get training data, like the input and output of a machine learning model. Second, we should choose appropriate machine learning method. And finally, we should use the machine learning model to training and prediction and verification based on new simulations and experimental data. So here in the following, I will explain this one by one. First, how do we get training data? We generate our training data simply by high throughput MD simulation. We choose 11 binary and 20 ternary silica-based glass systems. So this table lists all the binary and ternary glass systems we are calculating. So here, a green color in the box means the corresponding binary and ternary system was studied. We randomly choose their composition, so totally 500 different binary and ternary silica oxide were calculated. Then we calculate density and the modulus by MD simulation. We also did some benchmark tests, compare our simulation result and experimental result. So far, the MD simulation output, the density and the elastic modulus are generally consistent with experimental measurement. So right now, just pretend you believe me, our MD results are good enough. And then, in the next step, how do we generate input of our machine learning? But MD can give our output of our machine learning, but for input, here we found that MD can have similar rules. So all MD can be performed based on the empirical interacting potentials, right in this function shown on the left, which describe the interaction between any two atoms or ions inside this MD simulation system. So here the formula is the Q is for the charge, A and B and C in this formula is for the short range interactions. So we choose this parameter in the force field function as a feature parameter for descriptor construction as input of machine learning. Why? For two reasons. First, this feature parameter are easy to obtain. It's already there. As long as we know the composition and the type of ions, all this feature parameter can be obtained automatically. Previously, there are some machine learning models try to predict the glass property based on some structure feature parameter, like the average coordination number for some certain cation ion like silicon. So from scientific aspect, that feature parameter definitely makes sense and useful, but it is not practical if we want to predict a new composition. The reason is that no matter you want to experiment or simulation, the most time and resource consuming step is how to obtain the correct glass structures. If I already know the structure and the structure feature parameter, it will not take us too much time and resource to further calculate the density and the elastic modulus. So it is impractical to based on structure parameter to search unknown composition space. Another advantage for this feature parameter is the based on physics, because no matter densities and the elastic modulus, intrinsically they're based on the interaction between atom and ion in this glass system. So if we know how strongly these two atoms and ion can interact with each other in each glass system, it can introduce some physical information as input in our machine learning models. Then we use this feature parameter for MD force field and combine with concentration in different way. For example, we combine concentration and charge of different ion together, and then we also combine the concentration and the short range force parameter together. And also we do the multiplication between any two of them together. Totally we generate about 500 descriptors. That's our input of our machine learning. And then finally, what's the method we want to choose? So here we try different methods. We while we only talk about one method, we found it accurate and reliable. This method called least absolute shrinkage and selection operator with a gradient boost machine, in short name called GBM lasso. So it's a combination of GBM and lasso. So lasso is a special method that it can be used to determine automatically the importance of each descriptor. So here we can see that we have 500 composition, 500 type of output as elastic modules and density, but our input descriptor will also be close to about 500. If we use all descriptor with equal weight, we will easily make some problem like overfitting. So the lasso can help us to reduce this overfitting issue by only use those important descriptors. And then in this GBM method, it basically try to fit the final target by multi-step lasso, step together. Because lasso is based on some linear regression, so the GBM lasso can achieve some non-linear effect beyond the linear method. So with this method and the input and output, here we show our result for a regression. Basically means fitting result. So these three figures, the x-axis from left to right is the density, bulk modulus K, shear modulus G from MD simulation. The y-axis from left to right is the density, bulk modulus, and shear modulus from our GBM lasso machine learning fitting. We can see that in three figures, most data are distributed around this line of y equal to x. That means our regression fitting and our MD calculation are generally consistent with each other, which means our machine learning model have a very good fitting result. That's not surprising as long as we have many descriptors. The more important thing is to show us that our model have good prediction ability for unknown composition. To verify that, we randomly choose about 100 new composition, which including 11 ternary, 30 quaternary, 30 quinary, and 30 quinary compounds. We first input the composition into our machine learning model. Let our machine learning model make predictions first, and then we confirm that by MD simulations. In the bottom three figures, from left to right, is the density, bulk modulus, and the shear modulus from our GBM lasso prediction, which is again shown by on the y-axis, and then on the x-axis is our MD confirmation. So here I have emphasized again, it's prediction first, and then confirmed by MD. It's not simply fitting. And we can see still most data are surrounding around the y equal to x line, with about error like plus minus 10% errors. So we can see that even though we only train binary and ternary composition, we can accurately predict the density and the elastic modulus in a large composition space with many components, unknown component. So that is a very good result. We're very excited about this result. We submit this paper to MPJ Computational Materials, and we're free always ask hash questions. One question is that, okay, so far our machine learning model is fitted based on MD and confirmed by MD. But how do I know your machine learning is good enough to compare with experimental result? To answer these questions, we purchased a commercial database called SignGlass database. And from that database, we take about 1,000 data points, which is elastic modulus and density of multi-component silica-based glass. Then we first do our machine learning prediction if we know the composition. And then we compare those results with the experiment. This three figure from left to right is shear modulus G Young's modulus E, because experimentally prefer Mayer-Young's modulus, which can be obtained automatically if we know shear modulus and the bulk modulus. And then on the right side is the density. So y-axis, again, is our machine learning prediction. The x-axis is experimental measurement. Here I have emphasized again, these are true prediction because none of these experimental results were included in our training data. Here, different color means the number of such composition in that elastic property or density property region. So we can see that huge amount of data still surround this x equal to 1 line, which is the red dot line, with red dashed line, which means our MD machine learning prediction is still consistent with experimental measurement. So that have good prediction powers. More surprisingly, so initially, if you look on the left figure, you see that in the two dashed line circles, they show some outlier, which our machine learning are not consistent with experiment. Initially, we think, okay, maybe our machine learning is not good enough for those composition. But after careful check, we found that maybe not because our machine learning is wrong, it's because the experiments are wrong. Because this database, what they did is that they collect the experiment data from last 100 years from different peoples. So that there could be two group of peoples study same or similar chemical composition with different method. And one group people report one property, and then another group people produce another result property. And we found that for those outliers, our machine learning predictions are consistent with one type of peoples, but then are not consistent with another people measurement. So it's highly likely our machine learning and some experiment people are correct, but other experiment people are wrong, depending on different reasons. So if we remove these obvious outliers, we found that our accuracy still about 10% compared with experiment. For examples, compared with experiment, our prediction, like a root mean square errors for Young's modulus E, is about 6.67 GPa, so which is shown in the middle. So the average Young's modulus is around 70 GPa. So we can see that our accuracy still is like with about 10% errors, which is still pretty amazing. Imagine that we're searching huge composition space with more than 10 components, and we never including this data in our training set. So our result good enough compared with experiment, but then another harsh question from Refree is that in the glass community, there are already some well-established model to predict the elastic modulus, so-called model. In this model, you only need to input the density of glass, the dissociation energy of crystal oxide, and then Moore fraction. They automatically output the bulk modulus, and similar model output the shear modulus. So if this model works very well, why you bother to build another machine learning model? So we read the original paper, and we found that compared with the simple physical models, our machine learning model has two advantages. First, in this model, you still need to input the density of glass, which you either obtain by experiment or simulation, or use some other model to predict density. Another advantage is this simple physical-based model have an assumption that the interaction strength between different ions is mostly Coulombic interaction based on charge. This assumption is fine for some simple oxide glass, but if the transition metal oxide is included in the glass, this assumption may be inaccurate because we know transition oxide depend on d orbitals. There could be some kind of covalent features. So to verify this argument, we investigate the binary oxide of silicon oxide and yttrium oxide. So in this figure, the x-axis is a Moore concentration of yttrium oxide. The y-axis is a bulk modulus. We can see that no matter we use classic MD or ab initio MD based on quantum mechanics, or use our machine learning GBM lasso, the three type of results are always consistent with each other. On the other hand, if you use this classic model, no matter with this predict density or with this density calculated by our MD simulation, the results are quite different, inconsistent with this accurate MD or ab initio MD result. So this result suggests that our model by including the physical parameter of atom interaction into our input, our model can have better description for some complex physical systems. So here are our conclusion for this studies. We use descriptor based on MD force parameter and glass composition can automatically predict the density and the elastic modulus based on machine learning models. In the futures, what we want to do is that we want to use more accurate descriptor based on quantum mechanics and to predict some more complex property which cannot easily calculate by MD simulation. So here we are lucky. Why we consistent with MD and experiment so well is because one reason because the density and the elastic modulus are relatively simple physical property. They most depend on atom short range orders, not highly depend on long range orders. So that's why MD simulation with high cooling rate still get good result compared with experiment. So then their data, training data are very good compared with experiment. On the other hand, for some other property like decreased temperature, Dyer's constant, or toughness, those properties are depend on the atomic structure beyond the short range order, maybe medium order or long range order. So then we need some more accurate method like experiment direct measurement to get the property. So right now we are collaborating with professors from statistics department in Michigan to work on these problems.